So next radius ratio. Radius ratio is ratio of radius of cation and radius of anion. So ratio of radius of smaller ion and radius of larger ion. So generally radius ratio that is used to predict the coordination number of crystal lattices. So here on diagram form is there. Basing upon the radius ratio, we can predict the coordination number. If a ratio of cation and anion is up to 0.15, its shape is linear with the coordination number 2. If it is in between 0.15 to 0.22, shape is trigonal planar and coordination number is 3. If it lies between 0.22 to 0.41, shape is tetrahedral and coordination number is 4. If it is 0.41 to 0.732, shape is square planar and coordination number is 4. Then if it is 0.41 to 0.732, shape is octahedral and coordination number is 6. And if it is 0.732 to 0.99, shape is cubic and coordination number is 8. So radius ratio that is used to predict the coordination number. So what is coordination number? Number of atoms or ions present around a particular atom or ion. And all these are the examples. Coordination number of NaCl, CaCl. So here coordination number of silicon in SiO2 is 4. Whereas oxygen in SiO2 is 2. Okay. Coordination number of oxygen in SiO2 is 2. Okay. Then regarding all these topics, some objective bits. Okay. So I will discuss some objective bits here. First one is, which of the following is amorphous in nature? Okay. So generally solids are classified into two types, crystalline solids and amorphous solids. Crystalline solids are long range order solids, whereas in crystalline solids all the atoms or ions and molecules, constant particles are arranged in a order. That's why they are long range order. And amorphous solids, no order is there regarding their arrangement. So irregular arrangement in amorphous solids. Okay, short range order. So out of quartz, copper sulfate, salt and dry ice, fused silica glass. So out of this, amorphous solid is fused silica glass. Remaining are crystalline solids. Fused silica glass. This is an amorphous solid where there is no regular arrangement of atoms is present in that. Okay. Then second one, which of the following is covalent solid? Okay. So coming to crystalline solids, all the crystalline solids are classified into different types. So 4 types are there: ionic solids, molecular solids, covalent solids and metallic solids. So which one is covalent solid here? So these are the options: iron, diamond, NaCl, copper. Okay. So iron, copper, these two are metallic solids. NaCl is ionic solid. Then diamond is covalent solid. Okay. Then among solids, highest melting point is exhibited by. Okay. Next bit. Highest melting point is exhibited by. So different solids are there: amorphous solids, ionic solids, pseudo solids, molecular solids. Okay. So amorphous solids, low melting points, whereas crystalline solids shows sharp melting points. Ionic solids and molecular solids, these are the crystalline solids. Okay. Here ionic solids, comparison between ionic solids and molecular solids. Here pseudo solids are also like amorphous solids also. Okay. Then ionic solids and molecular solids. In between ionic solids and molecular solids, ionic solids exhibit high melting point. Why? Because molecular solid shows lower melting point. They melt below the room temperature. Okay. So that's why ionic solids, they exhibit the high melting point. Then dry ice is example of ionic solids, molecular solids, covalent solids and metallic solids. Okay. So dry ice. So dry ice, that is a molecular solid. Okay. So it is molecular solid. Dry ice is molecular solid. Then number of points at the center of primitive unit cell is. So you know about the primitive unit cell having only corner points. So 8 corners are there and having 8 corner points. No point is at the center of the unit cell. Okay. So no points are present at the center of the unit cell. Okay. So number of points at the center of the primitive unit cell is 0. Why? Because it contains only corner points. Okay. Next one is, here match the following. Unit cell and number of atoms are points per unit cell. So unit cell, simple cube and FCC, BCC. Number of atoms or points per unit cell, here 1, 2, 3, 4, 2, 1 is given. So simple cube, number of atoms per unit cell is 1. Why? Because it contains 8 corner points. Out of 8 corner points, here only 1/8 part of corner point belongs to a particular unit cell. That's why 1/8 into 8, that is equal to 1. 1 corner point. So simple cube is 1. And FCC, it contains 8 corner points and also 6 face centered points. Out of 8 corner points, 1 corner point belongs to this unit cell. And out of 6 face centered points, only 3 belongs to this particular unit cell. Why? Because each face centered point is shared by 2 other unit cells. So total number of points per unit cell is 1 plus 3, so 4. So FCC 4 points. And BCC, number of corner points 8. Out of 8, it gets each corner point gets shared by 8 other unit cells. So 1/8 part of it belongs to that particular unit cell. That's why corner point per unit cell is 1 and center point is 1. So total number of points 2. Okay. So 1, 4, 2. So 3, 1, 2. So this is the option. Okay. Next, the structural unit of crystal is called, just now I told. Structural unit of crystal is nothing but structural motif or structural basis. Okay. Then constituent particles in carborundum. So carborundum, this is a covalent solid. Okay. Carborundum is covalent solid. So covalent solid, it contains constant particles as atoms. So atoms are the constant particles present in carborundum. Okay, covalent solid. Number of lattice points present in unit cell of BCC and end center lattice points respectively. So body centered lattice. So body centered lattice having 8 corner points. Okay. So 8 plus 1. So total 9. Okay, 9. End centered, 8 corner points and 2 points at the 2 ends. So total 10. 8 plus 2, 10. So 9 and 10. Okay. Then in metallic lattices, the coordination number of metal atom. So coordination number of metal atom in metallic lattices, just now I told coordination number. So coordination number of metals lies in between 8 to 12. Okay. So here 8 or 12. Okay.